Let's consider a d-dimensional dataset with n data objects, and we want to project the dataset to a new space to maximize the variance of the projected data. We consider a unit vector u1 with unit length, and each data vector is projected to a scalar value, and the variance of their projected data can be given in this expression. The product of u1 transpose xi is the projection of xi onto u1, and similarly the product of u1 transpose x bar is the projection of the mean vector x bar on the vector u1. We then convert this form into another form in which A is the covariance matrix and x bar is the mean vector. We maximize the projected variance with respect to u1 under the constraint the unit length. Here we introduce a Lagrangian multiplier lambda1. We convert an constraint optimization problem into an unconstrained optimization problem. Taking the derivative of this with respect to u1 and set it equal to 0, you get to this, and then finally you get to this step, and the left side is the variance of the projected data where we saw before here. And in the previous step, lambda1 is the eigenvalue corresponding to u1, which is the eigenvector. So projecting data to an eigenvector with the largest eigenvalue will maximize the variance of the projected data. This page shows a numerical example. Given a matrix A, we can find the eigenvalues and eigenvectors. The first step is to find a characteristic polynomial and set it equal to 0 to get two eigenvalues, and from there plug in the eigenvalues to get the eigenvectors. You can use the eigen function in MATLAB to return the eigenvectors and eigenvalues from the same matrix. The results can be a little bit different because in MATLAB the eigenvectors are normalized. Assuming that we have unit vectors x1, x2 and x3. A vector z can be expressed in terms of x1, x2 and x3. Now we have new unit vectors u1 and u2. We can express z in terms of u1 and u2, but how much? So the portion on u1, we say it's z1. So z1 is the dot product of z and u1, and because u1 is a vector of length 1, so basically you have the norm of z times cosine of the angle between z and u1. And similarly, the position on u2, which is z2, is the dot product of z and u2, and it is the norm of z times cosine of the angle between z and u2, which is beta. In general, a covariance matrix can be decomposed into eigenvectors and eigenvalues. The matrix U contains eigenvectors on the columns, and the matrix V contains eigenvalues on the diagonal. We can select k normalized eigenvectors as a transform, and k is less or much less than the number of dimensions d. Then the projection in the PCA domain of the data for each point or vector. The projected point is the matrix product of the transform formed by the eigenvectors on the rows and the original point. So the dimension of the transform is k by d, and the dimension of the original point is d by 1. The dimension of the transformed or the projected vector or point is k by 1, and k is much less than d. If the number of dimensions is very large, then you may have the out of memory in computing the covariance matrix. Then you can compute the covariance matrix of sign n by n instead, and from there you get the eigenvalues and eigenvectors lambda I prime and ui prime, and from there you get lambda I and ui, as you should have with the d by d covariance matrix. And here is an example of PCA application in operation using stock data that you can see. Here 3 stocks time series can be considered as 30 variables. You compute a 30 by 30 covariance matrix, and from there get 30 eigenvalues and 30 eigenvectors. You select a number, small number of eigenvalues and eigenvectors, then project the original data on the small number of eigenvectors.